I often think it's helpful to come up with a lower bound on the answer you're expecting to get and an upper bound on the answer you're expecting to get before you really dive into the problem, so you put up those kind of guardrails. So what would you say is a lower bound on the average value of the function? Well, an average can't be lower than the lowest thing in the data set, right? So we could just say the smallest value of the function, at least on the interval that you're interested in. And then how about an upper bound on the average can't be larger than the largest value, right? But when we're doing this, I don't mean we have to compute these smallest or largest values with high precision. It's okay to just eyeball it from the graph. You don't have to be super careful about it. Because we're not expecting the average to be right close to that lower bound or upper bound anyway, so extreme precision in those is not needed. The upper bound in particular often helps catch the problem of forgetting to divide by the length of the interval. Because if you forget to divide by a fairly large number, you're going to get an answer that's way too big, right? And above your upper bound in many cases. Let's do a quick example. How about the average value of x squared on 0 to 1? So first thing I would do is draw it, right? So 0 to 1, x squared looks something like that, 0 to 1. How about lower bound on the average? All right, lower bound on the average, LBA. Well, the lowest value is 0, right? So just 0. How about an upper bound on the average? Well, the largest value is 1. So remember, for integrals, for areas, I was doing bounds like the height times the width, the height times the width. Here we could multiply by the width, but then we would just divide by the width because that's what you do when you compute areas. So it's even easier to do upper bounds and lower bounds here because you don't have to do a multiplication even. You just kind of eyeball the max or min. How about a guess on the average? You do your lower bound plus upper bound divided by 2, and you get 1/2, right? So we're kind of guessing that the average is 1/2. And take a look at the diagram and think whether you think that guess is higher than the true average or lower than the true average. So what is that average? It's 1 over b minus a integral from a to b f of x dx. And then we'll make it specific to the problem. So it's 1 over 1 minus 0, integral 0 to 1 of x squared dx. And try to do this, like pause the video, run ahead of me, and then let the video run and see if we end up in the same spot. So we'd get 1 over 1, integral of x squared is 1/3 x cubed, 0 to 1. I'll just drop that at this point and I'll move the 1/3 out front and get 1 cubed minus 0 cubed, which altogether is 1/3 1 minus 0, or 1/3. And how does that compare to my upper bound on the average and my lower bound? Well, it's above my lower bound, it's below my upper bound, and it's roughly equal to the guess. It's a little bit lower than the guess. Does that kind of make sense? Since we're spending kind of more time below 1/2 than above 1/2, you would expect that the average would get pulled down, and we don't have any extreme outlier kind of data points. Let's do another problem based on this. How about the average of x squared on the interval -1 to 1? Good thing to do is draw a picture, right? So it's our favorite parabola. well, some people's favorite parabola anyway. Do you even need to do any calculus here? I think you could reason by symmetry and say, well, we saw above that the average was 1/3 on this region, and then on the other region, on the other half of the, on the other side of the y-axis, it's going to be the same average, right? It's the same geometrical figure, just mirror image left to right. And then what's the average of 1/3 on this side and 1/3 on this side, and they have equal weights, equal widths. So we could just say by symmetry, the average is 1/3. So I often think that part of learning to be a good calculus person is to know when not to use calculus, and I think reasoning by symmetry is a great way to do it.